All right, so our chapter 3 is about processes, which is really the main thing that a computer does or a CPU does when you think about getting things done. Yes, there's memory management and disk file system management and managing all the peripherals that really make for a complete experience. But if you kind of get your head around processes, you have the understanding, especially at the level of this particular course. I don't know that I can illuminate too much. Everybody's doing very well on the quizzes, and I think maybe the way I do them is, I don't mean it to be heavy-handed. I'd like you to at least look at the materials, and maybe the answers are published somewhere. I keep saying that because the grades are good. And for this course, that is really the level. Some of the code examples that the book gets into, we really aren't doing that in this course. But if you kind of have some of the basics, and I'm going to lean on a couple of tools we've already seen, our good old 8-bit assembler just briefly, and the Windows Task Manager. And there are tools like that for Ubuntu server. Linux has processes. They tend to be command line, or you can buy them off the shelf, maybe not so much proprietary but specific, not built in. But the Task Manager in Windows helps illuminate if you didn't understand some of what goes on. So, the chapter has these kinds of ideas. Do you understand the concepts all the way down to this idea, how does communication between processes go on? All right. And it's kind of a restatement, and sometimes I trip a little bit, using but I try to use their PowerPoints in case something important that needs illuminating, but they're just telling you where we're going to head. All right, so there are some different terms maybe for processes. Processes are things that the computer does. Sometimes they're tasks, sometimes they're user programs, maybe even services. In a batch system, back when I was a kid, you'd give a deck into the computer center, and they would run your job. And for my first programming back in '79, you would submit jobs. They weren't on cards, but they would wait for a while in a queue and then get processed. And so different names, but it's really the CPU, the computer, getting something done. They actually kind of then even talk about within a program the parts that make up the program. And for that, if you say, gosh, I don't understand even what they were talking about there, well, you've experienced it several times, maybe more than you want, and we're not going to do anything else this term with this assembler unless somebody really begs, oh, please, can we have another task that's inscrutable and works hard. But this, you've experienced this idea of having a place, this is the program that they get, a place for variable, text, and where it's going to store data. We talked about the idea of a stack. When you push a variable, it's going to go into memory where the stack pointer goes, and that's just reserved memory that we would want to be sure not to clobber. There's a place where the code's going to get stored, and there's something called a heap. And a stack and a heap, when computers running a heap, is when we need a dynamically allocated variable. We need some space, and so that's usually a lot of memory for a heap. In C#, say, when you define a string or an array or something, that information gets stored on what's called the heap. It's just where these variables go. The stack is usually a little smaller, a little more nimbler and special purpose. Really, it's sometimes used for inter-process communication. We've seen that. You can push something on the stack and get it off. But in the book, it goes into detail a little more about the different parts of a program. And it's all true. I don't know that we need this detail to understand, okay, the process just organizes itself and what it's getting into. So you ought to realize that most programs, right, or processes are passive in the sense the computer's not running all processes it can run all the time. Excel, for instance, something that's definitely a user-oriented program, doesn't have any activity in the CPU till you double-click on the EXE or hit the shortcut or something, and then the system starts doing something about getting Excel in there. There are some processes running all the time. One, or maybe the most important, is the kernel, which has the basic commands, but there's a ton of other things that are going on at the time. And so, so just if you double click or something, one program sometimes can spawn a bunch of processes as it tries to get its work done efficiently. So I'm looking here at Task Manager, and Task Manager gives you a nice graphic for the processes that are running. In this Microsoft Edge that I'm running, and I got several windows going, it's running a PowerPoint, and so there really are, and we can't tell a whole lot from here, but this thing that I'm thinking, oh, I'm running Edge, is really running 15 different processes as it's managing probably its connection. There's PowerPoint show, these tabs that are open, and honestly, who knows what else, and why there's a command processor as part of this thing, I really couldn't say, but it is there. If you're curious about processes and want to see more, what I'd recommend, sometimes, or if you're having problems, okay, and you're not sure, later in the chapter, it talks about whether maybe a program is CPU bound, disk write bound, network bound. What is, when things slow down, what is preventing my program? Why is it slow? A good place to go is use a tool like Task Manager, and they have similar ones on Macs and Linux, that goes to tell. And on the Task Manager, in the Performance tab, if you open the Resource Monitor, something we looked at maybe in that first about your computer, this is where you can really get a better sense for what's going on with the processes. Gotcha. And you can do it down to the level of who's using disk, who's using network, and who's using CPU. And then I guess the overview tries to summarize it all in nice handy graphics and like that. And you already know how to figure out which program's using the most. Processes are identified by process identifier number, and they do then spin off, and I'm getting ahead of some of the slides. Then when the slides talk about them, you ought to understand that the term thread is, when you start a process, it can start child processes that then are managed by the one process, or perhaps we have to wait to get a web page before the rendering can occur, and that kind of thing. So these threads are really the sub-processes, or the smaller bits that happen to be running for some of these. It takes a real wizard and a deep knowledge to, I do not know what the ACISC EXE does standing here, and why it's running, and why it helps. There was, it's something with Cisco though. It's Cisco AnyConnect, so you can see that. So it's probably what's keeping me with the secure thing, so I'm not going to delete it. There was a time in the very distant past, maybe the 80s, when you could boot up MS-DOS, and you could identify every process that was running. You had command com, that's the kernel, and if something else is going. Now things are so complicated, you don't just cavalierly say, well, I don't know what that process is, so let me delete it, but you can stop the processes as they go on here. I'm going to look at the memory tab here a little bit and do something. I want to talk about what page faults are. Okay, so we talked about, things aren't, everything the computer can do isn't running, and everything that, even when you run a program, and I'm going to run Excel here, the whole program doesn't come into memory. So if I do Excel here, and I hope I can catch it up. Oh, I didn't want that. I was hoping, so Excel EXE, well, it just did have one page fault there. I had it open earlier, and what a page fault is, let me try blank notebook. I was trying to get it to do some page faults. Let me start Word. I didn't have that open earlier, and I guess Word didn't. But what a page fault is when the part of the program that you've asked for isn't in memory. That part of the program needs to be, quote, paged in, brought into memory, because the CPU can only execute the program when it happens to be in memory. And it doesn't bring in all of Word or all of Excel, just those things that it needs. And so there's that term for page fault. And you can see in the memory tab how much is committed and how much is working, and things like that. So let me go here, and I want Excel on the screen. Not a lot of drama. Notice these threads. The real work is the things that spawn out. But let's get back, and I think I've anticipated some of the slides. But you start programs, and the CPU takes care of getting them into memory, starting to execute them, and one program would be several processes, and on a server, multiple users could be using the same program. That's an advantage of the server. I know some of you are in courses MINF 3650 or 2650, where an option, if you don't have Visio or Project or some of the tools you need, is to get a TechCat Solutions subscription. Well, that's me, and I run it. I've got a server in the cloud, and all it does is let you log in, and your fees don't quite pay for everything that it takes me, but I'm sort of running it as if I break even for the year, I'm doing a service for you and about 10 other schools across the country. Some I'm hosting software for, but the idea is one image, though, of the program then can be shared among multiple users. That's a fairly efficient way. When we all use Excel on our separate machines, we're totally using more memory just because it's each on our separate boxes, but our boxes don't care. We usually have plenty of memory for things like that. So, if you need a definition, usually this is kind of in the opposite order of this. Stacks tend to be high memory, and they're showing kind of the high memory down to 0. But when that program started, it's got some text things that are defined, that string coming in, some data, the area where we would put our variables we're using. Not a lot of drama, other than when you hear stack and heap, then they're talking about memory areas. And there used to be a common error that came up in memory controlled situations: stack overruns heap, and your program would stop. That would mean that so much was done in here that there was no more memory to, the stack overran the heap, and you can't have them all. A little bit like more common and object oriented, and I make fun of it around Thanksgiving, if you've looked at it, is the object not set to an instance of an object, a really inscrutable, until you've gotten to the object programming some to kind of react. You're just, I'm trying to run this program, and it says, failed object not set to an instance. But stacks and heap are parts of memory. There is a diagram, so a process is new, it's running, maybe it's waiting, maybe it's ready, maybe it's terminated, and they have a nice picture, and sometimes it will go among these states as interrupts occur, or it's waiting for input. So, I'm going to stop, and I'm going to wait, let something else come in. I think if we're clever, I can go over here, and we can see, and I'm watching for Excel here, and just going to kill it, and Excel terminated that quick. Okay, I couldn't find a way, and maybe to show a waiting or some of the others. But the idea is, they're not making that up. That's what happens to processes. You can kill them in the. I'm going to do it. Here's a little bit better. If you ever have a rogue process, you can end the task here also and find some things. Right? And so, yeah, Word's not a problem. I can just kind of get that back going. So no drama. All it's really saying, they're kind of maybe illuminating what's in the chapter. You ought to be familiar with the term PCB, and it doesn't mean the poison pesticides. Maybe that was PCP. No, PCP is the drug. PCBs was the poison pesticide. But it's also, in our world, it's a program control block, and you can kind of think of that as the what part of this machine is allocated to a particular process. We have registers, we have memory locations we're using, and so you can think of that as this is your allowed area, kind of this is what you can work on, memory limits, and the operating systems make sure you just don't get outside of those. So when somebody says a PCB, okay, that's part of the kind of the rules, the law, if you will, or your availability of resources, and it's just kind of diagramming here, and to me it's a little more detail. I kind of could picture this, but if a process is running and I've got to kind of yank it out of memory to put another one in, I've got to save its state somewhere, and so I save the process 0 state, and then I reload process 1 state and bring it in, and then we swap back and get back to process 0. So that is an operating system, does add some overhead as it's managing all that. The chapter does here in a little bit talk about phones, which are simpler operating systems, but getting more complicated. Like I said, iOS, I don't know if it's true anymore. Maybe when this was written, did one process at a time, and Android sort of did multiprocessing, but now these guys multiprocess, and it's we're almost getting to hook up a keyboard and a monitor to your phone, kind of like you can kind of do to a Surface or a tablet or something, and you have plenty of capability. But the idea is, the PCB just helps the CPU to keep track of where it is. Okay, I've already jumped up on threads, and a thread is, think of it as a subprocess. Okay, but something that the process says, go execute this. If you think about just then managing threads or writing and I'm saying managing it, we're not going to do it. Managing multiple threads, you're almost like a manager of a project, or you're trying to put on, maybe a luncheon or something, and you kind of need to, reserve the room. That's one thread. You need to maybe arrange the sandwiches, get a speaker, and things like that. And it's important that you gather all those threads, and if one of the, at the right time, and if one of those threads fails, then perhaps your whole process will fail. And so it's the principle is pretty clear, and we do not need for this class. The book kind of goes into, well, here's the C structure for managing all this. Which you can take, you can ignore it, but realize, we need data. If there's a process ID, we need to save that somewhere. We need information about which thread, which process it belongs to. What we don't need to do is remember how a C program would organize that. Okay. We don't see it, but the CPU is constantly switching among tasks. We also have multiple CPUs, so that's almost like meta threading, where we can have several things going on at one time, and there are different queues. Queue is just a waiting line, and we can see all the processes in the system. There are ways you can see sometimes, and it's more of a disk thing, where, or maybe it's in storage, where you can see like queued up, and you can see that disk queue just goes up just a little bit. That's how many requests are waiting to, okay, I haven't been resolved. If you're having a problem and your disk, file writing bound, then often finding which disk and then maybe which process is consuming most of the is most of the read-write is a good way to then back into, maybe I can do that. But it's, screen record is the most active now, but I'm really don't have much of a disk queue, and it's not really active. Right now the disk isn't, but the idea of a queue is a waiting line. It's a request that's not getting resolved yet, kind of like waiting in line at Popeyes for your chicken sandwich, right? But you don't have to knife sand it. And so we were really looking at a device queue there. And I don't know that we can really see the ready queue using Tasks Manager, but it's kind of, I'm not running yet. Maybe if I loaded down the system a little bit more, we could see it. And so it tries to give pictures of how all that is managed. The details of management are important to us, and they've probably changed in some detail. They depend heavily on which operating system, which flavor, which version, and in fact maybe what you're trying to do in terms of, if I wanted to manage at this level, and you need a few more courses, including probably 2 or 3 in assembler or machine code and some other things. So yet another diagram, and just the kinds of things that will take something out of its paces, right? And say, okay, I've got to go out for a while because something else is an I/O request. Maybe your time slice ended. You're in chapter whatever 1. The CPU is saying, okay, great, you can run, but I'm going to yank you back after a while because I don't want you to run out of control. That's a time slice empowered. Forking is dividing into and adding a thread, or maybe we have an interrupt that I'm trying to read from the web, and that the page hasn't come back. So that all of those cause queues, waiting lines. And there's a whole great theory about queuing and waiting and managing that we won't need to get into here. But it's a beautiful kind of set of theory how to minimize the time and rules for doing this scheduling. So I don't know that it's important to say that be able to say, gee, I can discriminate between a short-term scheduling problem for the CPU or the long-term scheduling problem for the CPU. But short-term is really these things that are running. Let me manage those. And, while I'm doing all this, I've got to knock on the door. We want something new, right? You're busy and the telephone rings. That might be your long-term schedule says, well, am I going to answer that? Or ignore it. And we talked about bound processes. And so if you have some stalling, you can look at it. Most computers, just among us, with the kinds of work we're doing, especially these VMs, the thing I see most of the time, if you're having a real slow response, it's disk bound. And it's maybe a disk full. When a disk gets above 90% full, you might say, I still have 10 gigabytes on a 100 gigabyte hard drive, but above 90% full, it starts thrashing. It can't find the right space anyway. And it might also be network bound, and what the long-term schedule would like to do is make sure there's a good mix, right? If we have some disk-intense activities and some CPU-intense activities, let's get both of those in there at the time. And how does it know? Well, it's looking at it. You're going to install SQL Server and MySQL, I think in this assignment coming up. They're just database management systems. But in a DBMS, especially SQL Server has a very good one, when it gets a query, find all the records for customers in Mississippi who ordered horseradish or something, the first thing the database management system does is analyze that and tries and comes up with separate ways to resolve that. There's more than one way to handle a query in the DBMS. It takes a few milliseconds to do that, chooses what it thinks is the best, and then goes on. Operating system is doing that too. We talk about it running our processes, running Excel. It's also spending a lot of time figuring out what's the most efficient way to do this thing. And they've just pushed F9 to recalculate a big spreadsheet. I don't know if you know Excel, but you can turn calculations off. Sometimes it takes several seconds if you have this big model. And now I've got this CPU-intensive task all of a sudden. let me try to think ahead. And sometimes it'll guess wrong, right? Because it hasn't had much of that kind of activity. And you've been doing a lot of file saving with Excel as you're building your model and saving. So it gets the idea, oh, this is a disk intensive thing. So point is, it's pretty adept and getting more so. And a lot of the techniques of AI can come in to play, right? And so medium-term scheduling is this idea of swapping. So short-term, it's already in memory. How do I manage that? Long-term, do I let it in? How do I manage that? Here is the swapping out and swapping in, those page fault kinds of things. A little bit about mobile systems. Got to realize 2010, I think, 2011 maybe for the book. So the principles are all there, but the details of how iOS goes, I think, has changed mightily. Yeah. Similarly with Android, but they can have multiple things going on. You can only have one on the interface at a time, but I may be even wrong there. But mobile systems do multitask, and they're getting better at that. We kind of already talked about this in that PCB. That's a context switch, and so this is a little repetitive, or it's maybe coming up with the terminology that goes along with that idea of something needs to swap in. So I've got to remember what they're doing to kind of go out and then bring the other thing. It is some overhead. That's also why when your CPU starts getting utilized 80 to 90%, you're a little concerned because it spends a lot more time doing the swapping and managing than it does getting things done. And if you're trying to control a server, what you want to do if you're trying to troubleshoot that event is cool down some of those hot processes. The longer term as a system admin is maybe how to throttle those and just say, Excel, when they're doing a calculation, don't ever let it have this much, more than this much. Let the user wait, right? They go get a cup of coffee, and we need to keep the system alive. But that context switching, it does take some overhead, and that's when you see either the rainbow wheel of death on a Mac, or now it's the wheel, kind of like the hourglass, kind of the wheel thing, like you're spinning your wheels. Oh, I'm not getting anywhere, but the wheel thing has become, so you got to be able to start a new process, and you got to be able to terminate a process, and they're detailed. You could do that in code. We mostly do it by double clicking on something, and it understands from the extension what we want to do with that. And so if it's even a .txt file, it'll open up Notepad, but you can change that behavior. And so, if there's a process tree, then as the subprocesses and sub-subprocesses go, and there was somewhere along here that was said end task, but you could end the task tree. I think that was in Performance Monitor. If I'm looking here, if I wanted to do end process tree. So these are processes, if it spawned other processes, that will do sort of a cascading delete. If you're used to DBMS, just take all the things there. In a couple of assignments, something to look forward to. There are some tools for Windows in particular that let you take a deeper dive than you probably want. You don't have to do very much on the assignment. It's really let you know that they're there, but go into a deep dive on maybe what it's waiting for and that kind of thing. So, and I didn't even know that the App Store was waiting, and I don't need the App Store, but it's there just running as a process in the background. Something else on a Windows computer that you ought to be aware of is, and I think we maybe looked at the services, there's a services GUI that lets you kind of manage services. Some services run when they're triggered. Some are automatically started when you come up. In particular, on a Windows, VMware has some services that are running all the time, so they're doing some of the lifting when you're running a VM. So the service is kind of it is a process usually started by a machine when you start up, or Yeah, and I got the services in here and the monitor, or by a process that says, gee, I need this service to help, kind of support. And so now that's just there running all the time, maybe getting swapped out, maybe fairly idle till it gets called in, but it's got a little program control block that's holding on to its place in memory. So a process can start other processes and start other processes, and that's why you have thousands of processes going on, even when you sort of say, my computer's not doing anything. And yeah, kind of it's called a fork, and to do that, and yeah, and if you want to, you fork something, it's an exec command, more detail than we need. How do I make it happen? And we do not need to see this C# to have it happen, and nor do we need to see the Windows code. I'm sorry, it wasn't C#, it was C. We don't need to see the C code, but realize that you can write at that level and get processes going. Exit is sort of a normal thing, and abort is sort of an error termination. And we've kind of seen both of those in that OS flavor operating system. And I said, well, it was really just, it halted here and when it all worked, and it halted there otherwise, but that's really the idea. The idea is straightforward. It's just the kind of getting them as in the gestalt. Talked about the cascading termination, terminate the whole tree. That's right. And there's names. You got zombies and orphans. So if you just want to, kind of go around, yeah. So you have the zombie that doesn't have the parents terminated. It's an orphan. If didn't involve a weight, then it's a zombie, sort of a rogue. Those are named for these things. The way practically we handle those is turn the machine off and back on. Kind of one of the first 5 things if you're having a problem with something is turn it off and back on, and it comes. And it talks about how maybe Chrome has different things. You got the thing that actually pulls the page, you got the page rendering, maybe you have some plugins, and those are all just different processes. And so that's why they're for Edge, for Chrome. When I look at that server that I for MINF 3650 and look, there's the thing that's taking up some of the time, most of the time, is Chrome, because several students are using it, and Chrome is pretty bad, in my opinion, about spawning off and looking for updates, and sometimes half the CPU of that server for a few minutes is just finding out there are no updates for any students, but on it goes. Going to be a few slides on this idea of how do these processes communicate, okay? And so got to realize that, gee, I've completed something, maybe I've got to send back, or I found this answer I've got to send back. And so I might compete, computation speed up. I don't know how familiar you are with quantum computing, but the promise of quantum computing is this idea of almost infinite spawning without tasking the resource so much. So if you're kind of thinking, the security that's built into like HTTPS comes down to the problem of factoring a very large number that's a product of 2 primes. And doing that takes a long time. When you encode something, encrypt something to go through, you get the product of the 2 numbers, and when the person deciphers it, they have the 2 parts, and that lets them decipher it. It's a rough how RSA encryption works. But quantum could be that's a long process to take a big number, and on a box like we have, try this factor, try that factor, try that factor. It takes far too long to be able to try to break the encryption that way. But the idea of quantum computing is you could have almost an infinite number trying this at once and then reporting back. And anyway, it's getting closer, but on it comes. So you can speed up computation, but they need some way to go. And either it's like sending an email, okay, or shared memory. If you're a spy, there's a notion of a dead drop, right? A place where you're going to leave stuff or maybe receive your instructions. That's sort of the shared memory. we know where we're going to put this, or I'm going to leave the keys on the visor, and that's a shared memory idea. The message passing is more like an email or a text. I left the keys on the visor or under the seat. Not a lot of drama there, but they do show it in a picture, and so either I know where to look, or I've got a message that tells me what I need to know. How to implement that, again, we're not so worried about. And some processes could be affected by others, and they're waiting for something to happen. Others are just kind of cruising along, and nobody touches me. All the things that go along with Excel won't be bothered by the things that go along with Word, maybe until you try to insert something or bring it up. And there's some reasons that go along why you would do that. Convenient. The modularity is sort of this one use for thing. Break it down into a nugget, and then you can sometimes reuse those modules, sort of like a subroutine. And and sometimes, and this buffer thing is important because a lot of the waiting is having to do with reading that message that you've got. So if the messages are being sent faster than they're being consumed, there's the question of how big that inventory, the unread material could be done. And sometimes there's a physical limit, right? And the system knows it, in which case either the process it's sending has to stop or stall or delay till the stuff gets consumed, or perhaps the program breaks. That's the unbounded does just assumes kind of that we have all the buffer we need. I'm recording this, and the assumption there is that this screen recorder has it. You could probably put a thing, stop if you get to 5 gigabytes or something like that, but right now I think it'll record till it runs out of disk space. That's the idea of an unbounded or a bounded buffer. Nothing overly dramatic, pretty down to earth. We don't need to know how to code it. We just need to realize that whenever there's communication, there is this idea of handling yet something else for the operating system. And that's what shared memory is. We know where things are, part of memory, and yes, you get great. I don't think we're going to even get to 5, maybe. And you can see how they synchronize the process. And anytime you're passing a message, how do I know if that's been sent? There's semaphores and timestamps and that kind of thing to realize, am I getting the next best thing, or is this old and like a dirty read? Again, using a database terminology. And message passing is a little bit more like a ping, if you will. Here's what you need to know. There's that. Well, did they get it, and have they acted on it? And there's operators built into the kernel that let you do that. And so there's yes, a bunch of questions that the implementers need to handle. You could probably come up with those questions yourself, in my opinion, right? But there are issues, and so they've resolved them, and that's sort of the part of the operating system. We need to realize that it's there, but not necessarily worry about how would I make that happen or point to it in a system. And some terms used. So we've talked maybe about shared memory. Hardware bus is more like in registers. Network is through a network and ports. Synchronous is, gee, I send it and I can't move till they've gone. Asynchronous is we can work independently. Face-to-face classes were synchronous, 2:30 on Mondays anyway, and we're together. Asynchronous is you can look at the video or not, try the assignment whenever you like, and we do that because we have the shared memory. It's called the web, and you know where to link, and then ask some questions. So nothing too dramatic there. Little repetitive of the idea of an explicit message, direct communication. How do they establish the links? Usually they're sort of like a mailbox or by the PID, the unique ID. Yeah, it's a mechanism that is really not important to us. So I'm going to just kind of click through this. There are issues of what if there's multiple things I need to communicate with, and there are ways to manage it. So again, our view is it's handled if it's indirect, and understand or maybe at least be familiar with the terms more than the mechanism. Okay, and kind of jumped on this, but synchronous might get blocked. Asynchronous might not, but then sometimes you might not have as much certainty about the receipt and action on the message. But the blue terms or something, okay, I think if both are blocking, we have a rendezvous. Interesting. Okay. I thought a rendezvous would be a link up, but it sounds like here, if we're failing to link, but they're together. And some code of how to do that. Kind of doing a repeat of this idea of buffering, but you ought to understand, there's sort of an input and a pull, and it's got to be managed. Some cues that you got to get it right when it's coming, and otherwise you miss it. Instagram has a few seconds or some minutes. I'm not quite sure how that goes, whereas the text, right, lasts till I delete it. But anyway, it's a zero capacity. Gets into some POSIX, how POSIX is sort of the underlying of Linux and Unix, how it might handle that, and it's not so important to us. You ought to realize that much of the communication that goes on in a computer or system is done via the ports that are available. HTTP, right, or web comes on port 80. The SSH that you did when you went into Secure Shell, that is a default is port 22. And so a lot of times the way you set up communication is you have a listener on a port, and then if you want something, you send on that port, and that's really how kind of works. These processes sometimes can spin up, reserve these ports, and as long as the caller and server know that what port they're sharing, things work out. Sometimes you can change ports. There's no requirement that your server respond to HTTP on port 80. You can make it any port you'd like. You do confuse the bejesus out of all the browsers in the world, but maybe you're in an enterprise situation and you want some security. Our remote desktop uses port 3389 as a default, but you don't. That's not a requirement. So a little picture of how that dance goes between a client and a server, right? Getting a web page off of a server, then send a request, we get a reply, and then maybe we have this object we can share if we need, and some names for the ways they do that, and they'll try to explicate is you either have what's called a socket, that's like a port. RPC is like, sending a request to remote. A pipe is almost like a direct connection, and an RMI is a little like an RPC, but it's a Java thing. All right. So the way we've been working mostly is something like this. And I said, if you can't get it through your DNS name, say you were trying to remote desktop from your own computer into your server, then a way around it is to do it with an IP address and some things. So a pair of sockets, they're kind of well defined below 1024. Right? So 8443 for HTTPS, 22 for SSH, and I believe FTP, or is that user different? Anyway, there's there's just some standards. Above that, it's a little more wide open. The 3389 is a standard for remote desktop. If you're going to want to open up your SQL Server, I think it's 1433. Anyway, there are some quasi-standards for some of these guys. But it's the idea of knowing a DNS name, which translates to an IP address and a port, and handshake, and presumably they know what they're doing. A little bit about how to do it in Java. So an RPC is more of an abstraction. The connection is taken for you, and it's a little bit more like calling a subroutine to get that communication to happen. Okay, and there's this. You have to communicate there's a language for it in Microsoft to communicate with devices, and I'm going to just say this is all true, but boy, getting down to detail that doesn't help for our level of understanding, and we are kind of rolling into the end. And again, the symphony of back and forth. You ought to be familiar with these UML, Universal Modeling Language type diagrams, sequence diagrams. Sometimes it's a nice way to kind of display what goes on, but it's a lot of back and forth, handshaking, if you will, getting these things going. So, yeah, think of a pipe as almost like a direct connection, whereas a socket is something that kind of goes back and forth. And it's really just a way to open up communications. It's not literally a pipe. It's kind of a hardware implementation, and it's one way to, if you want to handle the communications rather than a socket, you say we're going to just name. It's almost like an area of memory that we're going to pipe, send it one to another. They also kind of call piping when you take the results of one command and push it into another, and that's the idea of kind of a pipeline. It kind of goes through the processes and comes out at the end. Not really, and you can name them, and that's about the only time I've ever really had any concern with named pipes is when you install SQL Server. It's a way to communicate. So a little bit of well click through, but a little bit of illumination. And so if those blue words you feel comfortable with, that's pretty much what you should take then from chapter 3. I'm going to stop this.